4D, we're differentiating h of x equals the natural log of e to the x plus 1. Recall that the derivative of the natural log of a function is 1 over that function times the derivative of that function. So in this case, h prime of x would be 1 over e to the x plus 1 times the derivative of e to the x plus 1. We find the derivative of e to the x plus 1 term by term. The derivative of e to the x is e to the x. The derivative of 1 is 0. So we end up with e to the x over the quantity e to the x plus 1. For e, we have the function y equals e to the 3x times sine of 2x. Notice that the operation between e to the 3x and sine of 2x is multiplication. So yet again we will turn to the product rule to give us the correct answer. So we differentiate by using the product rule. So that will give us the first factor times the derivative of the second factor. The derivative of the sine of 2x we'll find using the chain rule. That should be the cosine of 2x times the derivative of the inside function, which is 2, plus the derivative of the first factor, which would be e to the 3x times the derivative of 3x, that's 3, times sine of 2x. There's a little bit of cleaning up that we can do, but not much. I think I'll take out a common factor of e to the 3x, and that will leave us 2 cosine of 2x plus 3 sine of 2x. For f, we are asked to differentiate e to the 3x divided by the natural log of x. We're going to use the quotient rule. So that tells us that the derivative will be the denominator times the derivative of the numerator, which would be 3e to the 3x, minus the numerator e to the 3x times the derivative of the denominator. And the derivative of the natural log of x is 1 over x. We'll divide all of that by the denominator squared. Now, I want to simplify this a little bit. So I notice that there is a common factor of e to the 3x in this part and in this part. So I'm going to take that out as a common factor. So we have e to the 3x. Over here we're going to be left with 3 and natural log of x. And over here we're going to be left with minus 1 over x. Now, I would also like to get rid of this fraction within a fraction. That's a bit ugly. So let's do the following. Let's isolate the 3 natural log of x minus 1 over x so that we can work on that unimpeded, and then we'll put everything else together. So I'm going to rewrite this as e to the 3x divided by the square of the natural log of x times 3x minus 1 over x. These are algebraically equivalent statements, or expressions. Now here we need to find a common denominator. The simplest common denominator is going to be x. 1 over x already has that denominator. 3 natural log of x doesn't, so it needs to be multiplied by x over x. And that's what I've done here. Now that these two fractions have the common denominator of x, we can combine the numerators, and then the new denominator will be x, or the denominator of the resulting expression will be x. So again, we have e to the 3x over the square of the natural log of x, and then we'll have 3x natural log of x minus 1 all over x. Again, I think I'm going to pull this x over, I'm going to pull this denominator over to join this denominator. And so we'll have e to the 3x divided by x times the square of the natural log of x times 3x natural log of x minus 1. For g, we are to differentiate y equals the natural log of the quantity x to the 4th times sine squared of x, all divided by e to the 2x plus 1. The straightforward way of differentiating would be to write 1 over this expression and then multiply by the derivative of that expression. However, the derivative of x to the 4th, sine squared of x, divided by e to the 2x plus 1 is going to involve the product rule, the quotient rule, and at least 2 applications of the chain rule. So perhaps there's a different way of doing this. I'm going to first rewrite this natural log using some of the rules of natural logs that we have covered. And I'm going to get a collection of simpler expressions. So for instance, we can write this as the natural log of x to the 4th plus the natural log of sine squared of x. I'm going to write sine squared of x as sine of x squared minus the natural log of e to the 2x plus 1. Now I'm going to work on this a bit more to simplify this into even more basic expressions. So for instance, this 4 can be pulled up here to the front, and we'll get 4 times the natural log of x. The same with this 2. Let's write that as 2. Let's write this term as 2 times the natural log of sine x. And then here we have the natural log and e. Those are going to simplify to give us just 2x plus 1. Of course, it's subtracted. Now let's differentiate. We have a constant times a function, so the derivative is going to be the constant times the derivative of the function. We get 4 times 1 over x. We have a similar situation in the second term. We have a constant times a function. We'll differentiate by just bringing the constant down, and then we'll differentiate the natural log of sine over x. That will give us 1 over sine x times the derivative of sine x, which is cosine x, minus the derivative of 2x plus 1. Well, the derivative of 2x plus 1 is 2. Right, the derivative of this constant term will be 0. So I'm going to rewrite this again as 4 over x plus 2 cosine x over sine x is cotangent x. And we're done. For h, we are differentiating the function g of x, which is defined to be the integral from x to x squared of t to the 7th times the sine cubed of t dt. This may remind you a bit of problem 4a. But to use the method of 4a, we have to have a constant here and then a function of x there. So what I'm going to do is split this function up, this integral up, into 2 integrals. I'm going to integrate from x to a constant, and then from that same constant to x squared. I think I'll choose 0. It doesn't really matter which constant we choose, but 0 seems like a nice, safe choice. So we can split this interval up from x to 0, and then from 0 to x squared. And you may be wondering, how do we know that 0 lies between x and x squared? Well, we don't, but it doesn't really matter. This method will work no matter where 0 is, or which constant we choose instead of 0. Alright, now this is almost ready to go, except that we need the constant as the lower bound and the x as the upper bound. So I'm going to switch the order here. I'm going to make that the integral from 0 to x. And then the rest is the same. Well, except for one thing. When we switch the order here, remember that changes the sign, S-I-G-N, of the integral. So we need to indicate that by multiplying by -1. Now we're ready to differentiate. So this part is going to be similar to what we've done before. The derivative is going to be just x to the 7th sine cubed of x. For this part, we've got something similar. The only thing that's really different, other than this, the plus instead of the minus, is that instead of an x, we have x squared. That's analogous to going, say, from sine x to sine of x squared. The derivative of this would be just cosine of x. The derivative here would be cosine of x squared times 2x. We'd use the chain rule. We're going to need to use the chain rule here as well. So I'm going to substitute the x squared in for t, and I believe that would give us x to the 14th. 7 times 2 is 14. And then the sine cubed of x squared. And we need to multiply by the derivative of x squared, and that's 2x. Cleaning up just a bit, we get negative x to the 7th sine cubed of x plus 2x to the 15th power times the sine cubed of x squared. And there is possibly a bit more that one could do, but I think I'll leave it like that.